Hello. In the previous video, I gave a brief introduction, actually not as brief as I'd intended, but anyway, a brief introduction to, roughly speaking, what additive combinatorics is. And one of the things I stressed was that additive combinatorics is to some extent marked out from the other parts of combinatorics by the fact that the methods that are used are often not completely elementary. So they use tools from other parts of mathematics and they feed into those other parts of mathematics. Having said that, I'm actually going to start, because I think it's a good idea to start gently, I'm going to start with some arguments that are completely elementary, so some what you might call purely combinatorial arguments. And the first one, which I'll cover in this video, is a theorem of Plünnecke, which I'll state just as soon as I've shared my screen, and I'll give a complete proof of that, and that will be what I cover, as I say, for this video. So if I can find my screen to share, there we go. That was the end of last lecture. So let's have a nice fresh page. Let me state Plünnecke's theorem then. First of all, how do you spell Plünnecke? It's like that with a double N and an umlaut. And Plünnecke's theorem concerns sumsets, which I introduced last time, but let me just briefly remind you what a sumset is. So if I've got two sets A and B, I'll use this slightly more general setup. So A plus B means the set of all little a plus little b, such that little a belongs to big A and little b belongs to big B. Why don't we just have a little example first before we carry on. So if A equals 1, 2, 5 and B equals 3, 5, 10 or something like that, then A plus B, it's not actually maybe the best of examples, but we'll do it anyway. So the 3 plus 1 or 2, so that gives us 4 and 5, and 3 can also add a 5, so we will have to put 8 in a moment. 5 can add 1 or 2, so we get 6 and 7. We get 8 from 3 plus 5, and then we can't get 9, but we can get 10, and then we can get 15. I think I must have missed something out because I was expecting to have about 9 numbers there. So I've missed out 12 because I get 10 plus 2 and of course 11. So there we go. The reason I said that wasn't such a great example was that all the possible sums here are distinct, but that's perfect. That is something that can happen, so I won't bother to give another example. Now Plünnecke's theorem concerns the following question, or I will give one statement of it, but later on what we'll actually prove is slightly more general than what I'm going to state. So here is a nice theorem. It says that if A, or I prefer to say let A be a finite subset. I don't know whether Plünnecke actually stated it in quite this level of generality of an abelian group. It may be that Plünnecke only stated it for integers, but the proof that I'm going to give works equally well for in this more general setup. And suppose that either A plus A or A minus A, so I'll just write that as A plus or minus A, it's your choice, has size at most C times the size of A. Then, for any R and S, greater than or equal to 0 and not both 0, maybe I won't bother writing that, but for any pair of integers R and S, we get that any sensible pair of integers R and S, perhaps that's what I'd like to say, we get that the size of RA minus SA is at most C to the R plus S. times the size of A. Perhaps I should just remind you what, I can't remember actually whether I even defined it in the previous lecture. So RA just means, you could either define it inductively, so it's A plus R minus 1A when R is bigger than, when R is at least 2 or something like that, and 1A just means A, or we can define it more explicitly. It's the set of all A1 plus AR such that for all I, AI belongs to A. So RA minus SA is just what it says. It's the set RA minus the set SA, or explicitly it's the set of all expressions of the form A1 plus up to AR minus AR plus 1 minus all the way up to minus AR plus S. So the idea is that, if you remember from last time, we regard a sumset or a different set as being small if its size is only linear in the size of the set itself, when the set is large. And so this is actually, although this doesn't actually depend on C being a constant independent of the size of A, whatever that means, what we've got here is that if, we can think of it informally as saying that if either the sumset or the different set is not too large, then when you take some sort of iterated sumset and different set, that won't be too large either. That's what Plünnecke's theorem says. And if you've got time, I would strongly recommend just, for example, trying to prove for yourself a simple special case of this. So, for example, suppose even the following case was not completely obvious. This would have as a consequence that if, let's say, A minus A has size at most C times the size of A, then A plus A must have size at most C squared times the size of A. And I think you'll find if you haven't seen any proofs like this, and you try and prove that as an exercise, you will find that exercise extremely hard. Nevertheless, actually, the proof I'm going to give is not that hard. But when I say not that hard, I don't mean easy to think of. But I just mean not that hard to follow once you've been shown it. And actually, there's a story behind this, which is that Plünnecke's original proof, I don't know that much about it, but I think it was reasonably complicated and essentially rediscovered, although I'm not quite sure how similar the argument was, by Imre Ruzsa, who needed it for another purpose that I'll talk about later on in the course. And being a rather extraordinary mathematician, he just sort of found he needed it, and so he found a proof. But Imre Ruzsa's proof used a result from graph theory called Menger's theorem. And that's not a completely straightforward result. And the proof, even given Menger's theorem, is also not completely straightforward. And it used to be a little bit of a nightmare to lecture, because although all the steps were reasonably okay, just remembering the right sequence of steps was difficult. And then the proof I'm going to give is a proof due to George Petridis, who I'm proud to say was a research student of mine at the time. I'm less proud to say that when he first showed me the proof, it was so much simpler and more elementary that I couldn't believe. I didn't express my skepticism exactly, but I just couldn't believe that an argument of that kind could work. So I first read it basically sort of trying to see where the mistake was, and then it turned out there wasn't a mistake. And then that was actually very good news, because it meant that from that moment on, when people want to lecture Plünnecke's theorem, it's actually rather a pleasure to do so, and doesn't require anything like as much effort to memorize. So the proof, actually the main contribution of George Petridis was the following lemma, after which the remaining steps that I'll show you, there are a few steps after that, but those were reasonably well-known steps that I think were present in Ruzsa's argument, or similar types of arguments were present. So Petridis' lemma says the following. Let A and B be finite subsets of an abelian group. Actually, I'm going to call it A naught because it's convenient to do so, of an abelian group. and let k naught be such that a naught plus b equals k naught times the size of a naught. So all I mean by that is k naught equals the size of a naught plus b divided by the size of a naught. Then there exist a subset or non-empty subset a of a naught and a constant k less than or equal to k naught, such that a plus b plus c has size at most k times the size of a plus c for every finite set. Well, let's call it subset. So it's a subset of the same group, C of the group. I better write that in just in case it's not clear what the subset is a subset of. So I'll just quickly say once again, A has to be non-empty, because otherwise both of these it becomes a boring statement. Now, part of the reason I felt skeptical when I very first saw this argument was that the proof is of a kind that didn't seem to me like the sort of argument that works in additive combinatorics. It was a completely elementary argument. It works by induction on the set C, but it does work. So induction could say, if you like, induction on the size of C. I'll just say induction on C because I'm going to add an element to C and then assume it worked before we had the element added. Since you can produce any set you like by repeatedly adding elements to the empty set or any finite set, then this is a form of induction. So if C is empty, sorry, I've got to say what A is first. So actually I'm going to get rid of this induction on C. I will be using induction on C, but that will be after the first step, which is pick a subset A of A naught non-empty such that the size of A plus B divided by the size of A is minimized. And let K be the minimum. So we get that A plus B has size or equal to K times the size of B, and A dash plus B has size at least K times A, I should have written that, very important, and A dashed plus B has size at least K times A dashed for all A dashed subset of A naught. Right. So now I want to prove by induction on C, we shall show that A plus B plus C is less than or equal to k times the size of a plus c for all c. And now, if C is the empty set, then what does that tell us? It tells us that the size of A plus B must be at most k times the size of A, but that's exactly what we've written here, except we've got equals rather than at most, so no problem at all there. So now, assume the result for C. And let x not be in C. So x is some element of the group that does not belong to C. So what we'd like to show is that the size of A plus B plus C union x is less than or equal to k times the size of A plus C union x. I won't write that down, but that's just the target. We want to prove this same inequality here when we replace C by the set C union the singleton x. What I'm going to do is just look at each side in turn and see what we can say about it, and then we will deduce that we have this inequality. So the size of A plus C union x equals the size of A plus C plus the size of A plus x. So what have I done here? I've just said we take all sums of the form something in A plus something in C. We take all sums of the form something in A plus x. That gives us this and this. But there's been some double counting, because every time I had a sum A plus x that was already in A plus C, I counted it twice. So I must subtract something. So I'm going to subtract A dashed plus x, where A dashed is the set of A that led to a double count, so such that A plus x already belonged to A plus C. So far so good. And then we can actually slightly simplify that, so why don't I do that? That equals A plus C. A plus x is just a translate of A, so it has the same size as A, and similarly A dashed plus x has the same size as A dashed. Now let's have a look at the left-hand side in a similar sort of way. So we'll have that A plus B, or when I say the left-hand side, I mean the left-hand side with the modified set C, the slightly expanded set C. And that is equal to, I'm going to put less than or equal to here, actually, because that's what all we're going to be able to do. So it's less than or equal to A plus B plus C. So that's the elements of A plus B plus C. And then I also want the elements of A plus B plus x. And now I can take away anything that I've overcounted. And if I've got something in A dashed here, that means that that A dashed plus x belonged to A plus C, which means that when I added something in B, I got something in A plus B plus C, which means I overcounted it. So I can take away things in A dashed plus B plus x, and notice that A dash plus B plus x is a subset of A plus B plus x. I didn't make that completely clear, but let's just quickly put that in. So it's a set of A belonging to A, such that A plus x belongs to A plus C. So all these elements here did in fact belong already to A plus B plus C, so I overcounted them here. The reason I've only got less than or equals here is that I haven't actually guaranteed that I've taken away everything that I overcounted from this set here. I might have, so this could actually be a strictly greater than a plus b plus c union x, but that doesn't matter because I want to get an upper bound for the size of a plus b plus c union x. And let's see how we can bound these. So a plus b plus c, well, that we've got, we're assuming the result for c. So by induction, that's less than or equal to k times the size of a plus b. What about a plus b plus x? Well, that has the same size as a plus b, and we already know that the size of a plus b is k times the size of a. And what about a dashed plus b? So this has the same size as a dashed plus b. Well, let's just go back to what we know. We also know that a dashed plus b has size at least k times the size of a dashed. So since we're going less than or equal to, we can subtract something that's a little bit smaller than we, so we can get to that. We can put in here minus k a dashed. But that actually equals the size of a plus c union x. So we have got the inequality we wanted. This thing here is less than or equal to k times this thing. So we've completed the inductive step since x was an arbitrary element added to c, and therefore the proof is complete. Now that really is the result that's going to drive the rest of the proof. Just to convince you of that, let's see an immediate corollary, or maybe not quite immediate corollary, but so if a plus or a naught plus b is less than or equal to k naught times a, then there exists a in a naught, non-empty, k less than or equal to k naught, such that a plus rb is less than or equal to k to the r times the size of times the size of a. I just think that's a. We're going to get there. Maybe it's b. I'm suddenly a little moment of crisis, but let's just see how we get on. Less than or equal to k to the r times the size of a for all r in natural numbers. In fact, it's going to have to be the size of a because we've got an a on the right hand side here. Sorry, there's a moment of loss of belief in what I was writing, but it's come back again. So so pick a using the lemma just proved. So we now know that, just to remind you, we know that a plus b, pick a and k. We know that the size of a plus b plus c is at most k times the size of a plus c for all c. And now we're just going to apply that. We've got that, so then I'll do this slightly informally. One can write down a formal induction, but a plus rb equals a plus b plus r minus 1b. Now we use the lemma for this. That's less than or equal to k times the size of a plus r minus 1b. So I'm taking c to be r minus 1b. And we can just carry on this process. So by a similar, by doing exactly the same thing, that's less than or equal to k squared times a plus r minus 2b. So again, I sort of peel off a b, leave myself with r minus 2b, and I end up having to multiply by k, less than or equal to dot dot dot. And we see that this 2 add plus this r minus 2 always makes r, so I'll end up at when I finish the process with k to the r times the size of a, as claimed in the statement of the corollary. And let's just quickly get a corollary of the corollary. So I won't actually write it formally. So to note then that if b equals a naught, then we get that RB size of is less than or equal to, well, sorry, the hypothesis that if a naught plus a naught has size at most k naught times the size of a naught. I just see that I should have had an a naught up there as well. Then R a naught, the size of, is less than or equal to a naught plus R times a naught, or a plus R times the size of a naught is less than or equal to k to the r, or k naught to the r, because k is less than or equal to k naught, I'll stick it with k naught to the r, times the size of a naught. I'm jumping a step, so k naught to the r times the size of a, which is less than or equal to k naught to the r times the size of a naught. So we've already got here a rather important special case of Plünnecke's theorem, which is that if you have a sum set that's at most k naught times the size of the original set, then when you take the iterated sum set, r times, then you get a similar sort of inequality, but with k naught replaced by k naught to the r. A slightly strange aspect of that is that if I apply that when r equals 2, I deduce from the fact that a naught plus a naught has size at most k naught times the size of a naught, that a naught plus a naught has at most size k naught squared times the size of a naught, which is not terribly interesting. But one way of seeing that it is, I mean, not that that conclusion is interesting, but that that's not a sign of a defect of the proof, is that if I take b to be minus a naught, I can deduce the same conclusion. And then it's not trivial that you get a bound for a naught plus a naught from a bound for a naught minus a naught. All right, so now we've got a statement that tells us about sets of the form RB and how big those can be. But for Plünnecke's theorem, we want something like RB minus SB. So let's get another corollary. But before we do that, we need an extra tool, which is called Ruzsa's triangle inequality. Right, I'm going to state something that doesn't look at all like a triangle inequality, and I'll actually give the proof. Once I've given the statement and the proof, I will say a little bit about why it's known as Ruzsa's triangle inequality. So the statement is the following: let U, V, and W be finite subsets of an abelian group, as always. Sometimes people call these additive sets, so as not to have to keep writing finite subsets of an abelian group. Although I suppose one needs to say slightly more because we've got to emphasize that they're subsets of the same abelian group. Then the size of U times the size of V minus W is less than or equal to the size of U minus V times the size of U minus W. Maybe if you sort of screw your eyes up and stare at that, you can sort of see it, slight sort of triangle inequality flavor. That's a little bit like distance from U to V, distance from U to W, or something like that. But I'll talk about that a bit more in a moment. Proof of this is not hard at all. Let's, for each x belonging to V minus W, we're going to pick, however you like, Vx belonging to V and Wx belonging to W, such that Vx minus Wx equals X. We know that they exist. That's the definition of V minus W. They're not unique, but it really, surprisingly in a way, doesn't matter how we make the choice. We don't have to make it in some nice way, we just make it in some completely arbitrary way. And now define a function phi from u cross V minus W to u minus V cross u minus W by phi of ux equals u minus Vx u minus Wx. So notice that V and W were well-defined functions. Okay, by that I mean there isn't a unique choice of Vx and Wx, but I'm making a choice, and once I've made a choice I have well-defined functions Vx and Wx. For each x I've uniquely chosen out of the possible ways of doing so, I've just made some arbitrary selection of Vx and a Wx that had this property. Now I'll be done. I want to show that the size of this set is at most the size of this set. I'll be done if I can prove that this map is an injection. And I just quickly check that. So if u1 minus v x1 u1 minus w x1 equals u2 minus v of x2 u2 minus wx2, then if we subtract the first coordinate from the second coordinate over here, then we get that, well, first of all I'm going to write x1. Subtracting the first coordinate from the second coordinate gives me vx1 minus wx1. Since those two ordered pairs are meant to be equal, then I'm going to get the same answer over here if I subtract the first coordinate from the second coordinate. So this equals vx2 minus wx2, and that equals x2. So we've got that x1 equals x2. And once we've got that x1 equals x2, we have that vx1 equals vx2, which implies that u1 equals u2. And if I'd wanted to, I could have used the fact that this coordinate equals this coordinate to get that u1 equals u2. And so we finished. So phi is an injection, and that completes the proof. If you've got an injection from one set to another, the second set is bigger than the first set. So why do we call this a triangle inequality? It's because we can define a distance as follows. Define distance from u to v to be the size of u minus v divided by square root of the size of u times the square root of the size of v. Now if we divide both sides of this by the size of u times the size of the square root of the size of v times the square root of the size of w, then we get that. So the Ruzsa triangle inequality is equivalent to the statement that the distance from v to w, so that's I had to divide by u times the root of the size of v times the root of the size of w, is less than or equal to, I'm assuming that the sets are all non-empty, is less than or equal to the distance from, let me write it as from v to u times the distance from u to w. Well, that's starting to look a lot more like a triangle inequality. The only slight defect with it is that we've got a multiplication here rather than an addition. If that really offends you, then all you need to do is redefine the distance to be the logarithm of this quantity, and then you'll get something where you've got addition on the right hand side. But by and large, most people don't feel the need to do that. We've just got a multiplicative triangle inequality rather than an additive one. Does that mean we've got a metric? No, it doesn't, because the distance from u to u, notice that, what is it? It's the size of u minus u divided by the size of u. So it's basically it's the constant that you have to multiply by when you take the size of the difference set and compare it with the size of the original set. So that depends a lot on u. So it isn't really a metric, but it's saying something like that. So the distance from a set to itself is sort of measuring how kind of additively closed that set is, and the difference between two sets is saying something about how the additive structure of the two sets relates. So the triangle inequality then is saying that if you've got one set, if V and W are both in some sense additively close to U, then they must be additively close to each other. Because this is not always small, it actually can be useful, even in the case if you want to show that duu is small. Sometimes it can be useful to show that the distance from U to V is small, because then the distance from U to V is small, the distance from V to U is small, and that implies that the distance from U to U is small. Now then, let's go back to where we were before. We'd got that if in this situation we had that the size of A plus RB was at most k to the R times A, and now I'm going to get a similar statement, but it'll be RB minus SB, and we'll get that with the help of Ruzsa's. We're going to look at the size of RB minus SB. This is telling us that A is sort of close to RB, and then our S is another integer, so we'll get that A is close to SB, and then using the triangle inequality we'll get that RB and SB must be, so to speak, close to each other. So here is the more general version of Plünnecke's theorem that I promised earlier on. Let A0 and B be finite subsets of an abelian group, and suppose that, so it's just the same hypotheses as before, that A0 plus B is less than or equal to K0 times the size of A0. Then there exist A and K such that for all R and S, the size of RB minus SB is less than or equal to K to the R plus S times the size of A. And A is a subset of A0, non-empty. Proof. So let A and K be as before. So I pick A to be such that the ratio A plus B divided by A is minimal, and then we know all sorts of things about from the previous results we've already proved. So by the earlier corollary, we have that A plus RB is less than or equal to K to the R times the size of A, and A plus SB is less than or equal to K to the S times the size of A. So now we're going to apply the Ruzsa triangle inequality. That's a U plus a V and a U plus W. So by the Ruzsa triangle inequality, the size of A times the size of RB minus SB is less than or equal to the size of a plus rb, which is k to the r times a, and the size of a plus sb, which is k to the s times the size of a, so we get k to the r plus s times a squared, which implies that the size of rb minus sb has size at most k to the r plus s divided through by the size of a. And that completes the proof of that. And just to see how we get the original Plünnecke inequality out of that, so in particular, if b equals plus or minus a naught, then we'll get that rb, well, we get that, let's write it as ra naught minus sa naught, because if I replace a naught by minus a naught, I'll get the same size of set here, so it doesn't make much difference, is less than or equal to k to the r plus s times the size of a, but a was a subset of a naught, so we get k to the r plus s times a naught. Also, what was the hypothesis? That follows from the assumption that a naught plus or minus a naught is less than or equal to k naught times the size of a naught. Let's put a little naught in there. So, well, I've actually basically finished for this video. I've now completed a proof of Plünnecke's theorem. And I think the thing to note about this is that every single lemma was rather easy. I think the first one, the one of George Petridis, was perhaps the one that would be hardest to think of the proof of. I think all the other ones, I think if you were asked to prove Ruzsa's triangle inequality, that counts as an exercise. But somehow putting all these fairly simple steps together and thinking of the right steps in the first place to put together amounts to something that's very much less obvious. So I find this a rather remarkable piece of mathematics. It's a sort of series of easy steps, but very much not an obvious series of easy steps. And we end up with a very non-obvious theorem. So if you did follow my little suggestion, I'd imagine you'll be in the minority, but if you did follow the little suggestion earlier on of having a go at proving a special case for yourself, I think you will have felt the difficulty and will appreciate that this was a rather remarkable argument. Do I need to say anything else? I think not. So next time I'm going to prove another rather remarkable result that also has a sort of fairly easy to follow but not obvious proof, which is called Khovansky's theorem, which is going to say something else about the size of iterated sumsets. So we'd be interested in the size of NA as A gets large. But I have finished for now, and thank you very much for your attention.